let's consider the parts that make up a PLC. The main part, or the core of the PLC is the CPU, the central processing unit. And the CPU unit in a PLC, we usually think of that as being part of the processor module that interfaces with program memory and data memory and performs the executions in program memory, storing data in data memory. And so this is kind of the brain of the PLC. And the interesting thing about PLCs is often this brain is its own module, and you plug other modules into it, like an input module or an output module. Some just daisy chain off to the side, some have backplanes where you plug in cards. There's a lot of different types. Now all of these things, the output, input modules, the CPU, they all need power, so there needs to be some type of power supply. And often the power supply is either matched to the PLC in the sense that it's almost integrated in, or it's off to the side and mounted very close to the PLC. The power supply typically just takes 110 volt AC and converts it to the 24 volts DC that most of the PLCs require. Now the other big piece of this that how can I say this? The PLC would be no good without the program that's in it. Okay, you can't just buy a PLC, turn it on, and it figures out how to control the machine you got. It doesn't work that way. You have to program it. So another big piece to a PLC system that actually makes it useful is the programming device, where you can write your program and upload it to the PLC. So all of these are pieces, and really the input and output module don't do you much good unless you connect it to something. So you need input sensing devices and then output load devices that the PLC can control based on what your program says to do, in reference to the inputs. Now, a really neat feature that I'll mention again later is that the inputs, if you think about it, they are electrical inputs and the outputs are electrical outputs. Well, the problem with that is it's pretty easy for wires to get crossed in an industrial situation and high voltage be put into an input module or be applied across an output module. And if there's not isolation, that can blow up the whole PLC. But in industry, and just every PLC I've ever seen, there is something called optical isolation, where there's no actual electrical connection between a portion of the input and the brain, the central part of the CPU or the PLC brain. And so that's true on the input and the output, and that helps protect the PLC, because if something happens where there's an over voltage or overcurrent situation and the particular input or output module is damaged, that module can simply be replaced fairly easily, and the process started back up. So PLCs are set up to be rugged and reliable, but when something goes wrong, they're also made to be repaired fairly easily. Now, architecture has to do with the PLC or the software or both, and there's this idea of an open architecture and a closed architecture. Open architecture is becoming more and more common. It's kind of like open source software. It's where it makes it easy to program one type of PLC with a different type of software. It's like having a standard where they communicate. Closed architecture is still more common, and what that means is that the design of the system is proprietary, and you can't just connect any other system to it easily. You can't just slap on an I/O module from one manufacturer to a PLC from another manufacturer. That's still not common, but it's starting to become a thing, and who knows, maybe it will catch on. I do want to mention, though, a couple of big names in PLCs are Omron, Rockwell Automation, or Allen Bradley. Those two are basically the same thing, and then you've got Siemens. But there's a big player in the field now that has really rocked the world of all the big names, and that is Automation Direct. Automation Direct has some off-brand PLCs that, while they are not, the absolute best, easiest to program PLCs, most rugged and reliable, they are pretty doggone good, and the nice thing is that they're dirt cheap by comparison. In the past, all the big players would charge you several $1,000s just for the programming software to program the PLC, which, I mean, it makes sense. The programming software takes time to write, it has to be updated and so forth. Well, Automation Direct came on the scene with a slick website where you could just, the prices were right there, you could order and get things in very quickly. They have very fast shipping, at least as of this recording this video, and it's been that way ever since I worked for Amatrol, which has been since 2007 or so. It's 21 now, so that's 14 years. And they have lightning fast service delivery. The software for programming their PLCs is free. and so they have really taken the market by storm by offering low-cost PLC hardware and free software. And it was interesting because all the other big players kind of followed suit, and you'll see their entry-level PLCs now have a reduced price point and typically offer free software. So it was a case where competition really helped the end consumer, because in automation a lot of times you actually don't care too much about the cost of the PLC and the associated input-output modules, because if there's a PLC there, the system and the process is probably valuable enough that that PLC is a small fraction of the cost of that process, and it's worth it if something goes down to just buy another part, slap it in, and keep going. But one of the big things you need is quick response time, and that's where the big names were sometimes lacking. And I think that's more the niche that Automation Direct filled, was not only the price niche, so they get people in the door early on because look how cheap it is, but also they offer excellent service in terms of delivery times and technical support and all those things. So anyway, so just a name you will hear and know as you start to become involved in automation, and just something you should be aware of. Fixed I/O is, how can I explain this? Some PLCs are modular. That means you can add on to them. Some are not. They're fixed. In other words, the number of input and output points on these PLCs is fixed. You can't change it. You can't add to it. You can't, well, I mean, I guess you could take away from it by blowing some of them up on accident, but you know, typically if you damage one input, you could damage multiples. But these are not made to be taken apart. They're just a fixed, they're also called a brick PLC. And basically the processor and the input-output modules are all just together in one box. They're just for small machines. They're not obviously made to be expanded. Some of them technically are expandable, which confuses the issue farther. But a lot of times these will have little displays on the front of them. They're more likely, if they're a brick or fixed I/O PLC, they're more likely to have a little screen on them, whereas expandable PLCs most often do not. But these are sort of all-in-one devices that make it pretty easy to implement a small PLC for just really small processes. Modular I/O, as I mentioned, is where you have a PLC and the power supply is separate, and you can stack modules onto it, and this really increases flexibility. Now there's a couple different options. Some of these are set up so that you basically daisy chain the modules on, and that's the way Automation Direct's PLCs work. Others are set up with what's called a backplane. It's kind of like having a motherboard in your computer, except the difference is that the PLC houses all the, you know, the processor and the memory and the, you know, all of those things, whereas the backplane is more just a circuit board, more kind of like wires on a circuit board for connecting the various modules. Now I will say that backplane PLCs are losing favor. They're not as common anymore as they used to be, but you may still find them around, especially in a process that's been running for, you know, 20-30 years. The power supply is the part that provides the DC power that the I/O modules and the PLC and all that needs. Now usually the power supply is not used to provide field power. Now what that means is you've got all these devices like input devices and output devices, switches, sensors, you know, solenoids. All these things require power to operate, and most of the time the PLC power supply is not sized to give power to all those field devices. That's not common, although it can be done, especially in smaller systems. But in larger systems, field devices get their power from some other source. Now I should mention, with power supplies you also have something called a power budget that you need to consider. If you know that you've got a certain PLC that pulls, you know, let's say a ½ amp or something, and you know you want to add on 20 different cards, and each one of those cards is going to pull a 1/10 of an amp, you better add up how much current that is and then size a power supply that has at least that much current capacity. Otherwise the PLC is not going to work because it simply can't get the power it needs from the power supply. So power budgeting is another thing that's very important, but I don't want to go into too much depth in any of this right now. So the CPU is kind of the brain, as I said. It runs the program. There's not an operating system per se like you might expect on a PLC. It's not like you connect to it with a mouse, keyboard, and monitor, and now you're, you know, cruising the web or something. I'm sure there are some like that out there, but that's by far not common. I suppose if you used a Raspberry Pi as a PLC, which some people do, then you'd have, a web surfing PLC essentially. But in industry that's not common because a Raspberry Pi is not really made to be rugged electrically, mechanically, thermally, all those things like a typical PLC is. But anyway, yes, it has an operating system, but it's not the type, it's not Windows or something like that. And basically all the operating system really does is allow you to talk to the PLC, upload programs to it, communicate information, force inputs off and on, things like that. Things that are, in line with the function of the PLC, not for a user interface. Now the way the PLC works is basically it performs a repetitive process called a scan. As we learn about ladder logic and how PLCs run their programs, we're going to have to get used to a different way of thinking about programming. If you think about a panel that just has a bunch of relays in it and you've wired it up and it's working, controlling a machine properly, and it's performing logic functions, well, all the relays can get power at any time. Okay? In a PLC, things are a little bit different, but you usually think of your program as if the whole thing is operating at the same time. Now that's not exactly true, but for our introductory purposes, it's close enough. If you're used to programming in other languages, like, I don't know, C, MATLAB, any, Fortran, any of those languages, you're used to your program moving through line by line, and if you put a delay in or something, the program just sits there at the delay and waits until that's done and then goes to the next line. Of course, you get into problems with flow control, and that's where flow charts come in and all that. But with a PLC, the way you think about it should be very different. Although technically what it does is it starts at the first rung of your program, which is kind of like a line. It evaluates that and then sets the output. It never waits very long. It never sits there at the line and waits for something to happen. It goes to check if something's on. If so, it sets an output and then moves on to the next line. If it's not on, too bad, we're moving on. So it does this thing called scanning, where it's basically executing the program. That's that green part of the arrow, what I just described, where it's evaluating what the output should all be on all the output cards based on the inputs that you have coming into the PLC, and obviously the program that you wrote that translates inputs to outputs. And things like, if the weight sensor is triggered, then you know that means the box is full, so turn on the motor to move that box out of the way. It's as simple as that kind of programming. But that's just part of the scan. That's usually the major part. That's the longest part, is the program, especially as the program gets longer. But there are other parts to the scan where it does diagnostics, communications, things where, maybe it checks for updates, it tries to see if something's trying to connect to it to update the program, things like that. Then what it'll do is it will write what the outputs were computed as in the program, read the new value of the inputs, because they may have changed since the last time, do the recompute, and then go through. And it just does this over and over. So it's kind of like it runs your program from top to bottom repeatedly. And the scan time is the time that it takes for one complete scan. Now that does technically include reading the inputs, updating the outputs, and all the diagnostics and communication. But we usually think of it as just being the time it takes to run the program you've written, because that's usually the major portion of it. So this is something that happens over and over, and you got to get used to the idea that these programs in PLCs run quite differently from the ones that run in a regular computer. The input-output devices are very important. Probably I/O is one of the strongest features of PLCs. I mean, technically, you could set up a home computer, just a PC that you would buy for, you can get free ones that are old that have more power than a lot of modern PLCs. Technically, you could set one of those up to run as a PLC. The problem you would get into is how, well, first of all, it's not ruggedized, but second of all, how do you get input buttons in? It's not uncommon in a machine to have hundreds of sensors that have to come into the PLC and hundreds of outputs. That's not unreasonable. In fact, you will see some in this class that are simulated that have upwards of 20 or 30. And you will be able to program those because you just deal with it one at a time and figure out, it's not all that hard, because what you really do is you kind of group them together. These certain inputs are more associated with those outputs. You write the program for that little part of the machine, and then you write a program for the other parts and so forth. And there's some crosstalk between the subsystems, but you can often break up the programming into smaller chunks, just like you would in any programming language. But the input devices can be things like push buttons or limit switches or even sensors that are non-contact sensors. And these things are wired into inputs. Now you'll notice in the diagram here, there is a field device power supply. As I said before, the power supply for the PLC often is not used here. This is another power supply that is used to provide power for the PLC. Now, in our class, we will probably use the power supply for the PLC to power the field devices just because it's more convenient to have a single power supply. In the real world, that doesn't happen all that often. Output modules, of course, allow you to activate things. Now, output modules quite often use a voltage that is higher. Now, here's where students get into trouble. Students see the output section and they think of these terminals. They begin to think of them as sort of a plug-in like in the wall, right? If I plug in my laptop, I can get power from the wall. That's not at all how output devices work on a PLC. Output modules on a PLC basically make contact. Okay, you can think of them as just a switch that the PLC can close, but there's no power there. So you still need field device power, and notice here we've got 200 volt or 240 volt AC that's being used to power the field devices. The only thing the PLC does is give each of the devices the other leg that it needs. I mean, look at it. L2 is connected to all of the field devices. The only thing that any one of these field devices need in order to come on is L1. It needs to be touched on the right hand side by L1. Well, the PLC has the ability to do that because look, the PLC has a wire coming into it that is L1, and it can touch that wire to any or all of those different output points and thereby turn on the motor starter, the solenoid, the two pilot lights, the red or yellow pilot light. Now notice another thing. Notice that L2 also goes to the output module. The reason for that is that very often the output module itself also requires power from the field device. The reason for this is because of the optical isolation I mentioned before. Some part of the input and output module is powered by the PLC's power supply, but only up to the point where it's either a sensor or a little LED inside that indicates whether the output should be on or off or the input is on or off. The other part of it, the part that actually makes contact and allows current to flow, needs power as well. So it's very common to see a setup like this where both sides of the field device power supply are connected to the output module to provide power for that other half of the output module. Same thing with input modules since they are optically isolated. Now this may not make a whole lot of sense right now. That's okay. As we go through the labs and I show you how to wire things, remember this. Just remember that you're going to probably make the mistake of thinking that you can just hook up two wires to an output module from a field device, and that output module will turn on power and make the field device go. Maybe you've got a small motor or something. Well, that's not the way it works. The power for field devices have to come from a power supply, not from the module itself. There's another thing to notice I didn't mention before. Notice on the top of this diagram it says output module. It's got 0, 1, 2, 3 all the way through 15. What those represent are light emitting diodes. One really nice thing about just about every PLC I've ever seen is that the input and output points where you would wire each sensor or each output device, each one of those points have a light emitting diode associated with it, so that when that output comes on, like if the PLC tries to turn on the motor contactor, for example, then the output number that's associated with that, which would probably be 0 in this case, that LED would come on, indicating that the PLC is trying to turn on that particular device, whatever is connected to that point. In the same way, LEDs are set up on input modules to indicate when sensors are triggered and on versus off. So this really helps a lot in troubleshooting PLCs. These diagnostic indicators are really, really useful because I guarantee you, when you write PLC programs, you won't get it right the first time, just like any programming language. As a matter of fact, I've been programming since high school, and it was only about 3 years ago I wrote my first program, and it was in ladder logic where it worked the way I expected the first time. High school for me, I graduated in 1993. I've been programming a long time in multiple different languages, okay? And this literally only about 3 years ago is in my home PLC system that is a really fairly simple program. It was the first program I've ever written, So let's see, what is it, 2001? That's what, 2018? So I've been programming for 18, it's 25 years. In 25 years, it took me that long to finally write a program that worked right the first time. Now, obviously, I've always worked on programs and debugged them to make them eventually work the way I want, but this was different. So don't think you're going to go in, write a program, and it work right the first time. The nice thing about PLCs is there's so many diagnostic helps to figure out why your program's not working. Plus, in my opinion, diagnosing PLC programs is actually pretty straightforward because the language itself is a pretty easy system. If you're a person, well, it doesn't really matter if you like electrical or mechanical systems more. By its very nature, ladder logic programs are pretty straightforward and easy to understand. In fact, another nice thing is that ladder logic programs are pretty much the same from brand to brand. Now there are minor variations, but the essential structure of the language remains pretty much the same. You've probably programmed in a couple of different languages by now, and maybe you've had MATLAB and, I don't know, Python. And they're both basically C-like languages, and yet there's enough differences where it can be frustrating. You might say, well, why can't they standardize on one language? We just program computers, all computers in one language. Well, there are multiple reasons why. A lot of times languages are really written for one particular application. That application kind of comes and goes, and then that language is pretty much dead. There are exceptions to this. COBOL, for example, is still in use, and it was a programming language, I think, built back in the 60s or so. I don't know the detail on it. I just know that my cousin had a husband, and he worked for a company that still had COBOL. He was a COBOL expert. He didn't use a smartphone. He didn't get on the internet. I mean, he was an old school kind of guy. He unfortunately passed away. And he was in his 60s and still programming in COBOL for a big company. And there are systems that are still working that companies can't do without. So some languages do hang on. And the generic form of ladder logic really has hung on for a long time. And I think the reason is because it's such an easy to understand language. Basically, you have something that looks kind of like a circuit. You've got two power rungs on either side. On the left side, that vertical, I shouldn't call it a rung, it's a rail. The rail on the left and the rail on the right are power rails. And then everything in between, the horizontal shaped lines, are called rungs. That's why it's called a ladder logic, because it looks like a ladder. But basically, power is trying to get, current's trying to flow from one side to the other. And you can tell it looks kind of like we've got a bunch of switches on the left that may or may not allow power to flow through to the output devices on the right. Those output devices, even though it's a set of parentheses, are made to look like an output coil of a relay, a circle. And so basically this is kind of like switches driving a relay coil. So this is very much like relay logic. And in fact, you can call it relay ladder logic. That is a proper name for this. Now, there's different features. For example, the things on the left that look like switches, they're not really switches, they are instructions. And what they do is they look at whatever particular address you give them, and these are not addressed yet. You'll see that a little bit later. But they look at the address you've told them to look at, and if it's on, they allow power to flow through. If it's off, they don't. Unless it's an inverting instruction. There's actually an example of that here, but we'll get into that later. If all the instructions are set up so that they're allowing power to flow, then whatever the output memory address is turns on. And this is just like, if all the conditions are met for a relay to come on, then the relay coil is powered. Now here's what some of the more popular ones look like. Here's the CLIC software that we're going to use in this class. It's the CLIC programming software. This is Automation Direct's product. They actually have a couple of different, at least one more and I think two more programming softwares, but they all look pretty much like this. You can see sort of the switches on the left hand side, you can see the vertical rail, you can see the rungs. On the right hand side they have eliminated the right hand rung, although, because it would be after, you see where it says Y005 set, the other rung would be to the right of that with an electrical connection, but most people understand ladder logic well enough to realize that that's not necessary. This is just made to kind of look like relay logic. But it just works the same way as any others do. If X002, which is input, is on, that's actually an inverting instruction. That's what that line through it means. If it's on, then no power will flow. But if that address is off, then power will flow through and turn on that particular coil, which is coil Y005, and then click that as a particular output point. But don't worry about those details right now. There's all kinds of commands on the side. It's a command palette that you can drag instructions into the code and write your code. The one interesting difference that I'd never seen before until I started programming in this particular flavor of ladder logic is that it requires an end instruction. Why they require that, I have no idea, but you notice the NOP instructions down, there's a bunch of rungs that just have nothing on them. Most of them are labeled NOP. That means no op, or no operation. It's pretty common in assembly language to have no op instructions. You don't have to worry about that. Basically, your program ends where that end coil is located, and by the way, you have to drag that end command into your program to end the program. Otherwise, when you try to send it to the PLC, the software gives you a syntax error. Here's another common one. This is the CX Programmer, which is used by Omron, another big name in the field. I couldn't find a good Step 7 diagram, and I don't have the Step 7 software, so I couldn't show you Siemens, probably most popular language. But this is Omron, which is still a big name in PLCs. And so you see the setup where you can see the right-hand rail, and now the left-hand rail is sort of blending into the line numbers on the left, but it's still there. You can see the rung set up, and if you understood the last program I showed you, you could understand this one too. There's not a big difference between the two. There's input instructions that basically look at addresses and either allow power to pass or not. You can see the slash through that jog work bit is an inverting type of instruction. It's more standardized. It looks more like what you would expect. And so I could probably pick up this software and in a day have a program written or troubleshoot a program because I understand ladder logic well enough to figure this out and be able to recognize most of it from the beginning, but then change whatever is not working. You see the output coils on the right look more like coils. They're at least a complete circle. I guess the parentheses probably came from a time when a lot of programming was being done via just ASCII text, and so all you had to indicate a circle would be more of a set of parentheses. Suppose you could use a capital O, but here's RS Logix 5. This is an older programming language, but it's basically Allen Bradley or Rockwell Automation's setup. And again, there's a few more complicated instructions here, but you can still see switches on the left. You can see output devices on the right. This does include some timers. Timers are technically output devices. We'll learn about all that a little bit later, but anyway, just a quick sampling of the various programs for writing ladder logic programs for different brands of PLCs. How do you write them? Well, in the past, people used handheld programming devices where you go up to the PLC, you'd connect it, and you could go through it. It was a very laborious process to change a program because the only display you had was this little LCD, liquid crystal display. Think about trying to program a PLC with your handheld calculator, right? Not even a graphics calculator, but a little scientific calculator. It was a big pain. I have never used one of these, and I hope I never have to. What I have always used is a laptop or a computer, a PC, with software like I just showed you on the last slide or so, that uses the manufacturer's software so that you can write the ladder logic program and then download it to the PLC, and away we go. So you'll probably never have to use a handheld programming device. I'll probably never have to. By far, computers are the more commonly used programming device for PLCs. The other nice thing about using a computer is that all the manufacturers I've ever seen allow you to not only program the PLC but monitor it while it is running. So you could leave the PC connected to the PLC, your computer connected to the PLC, and as inputs come on, the instructions on the rows will light up indicating that that input is on, and as the PLC decides to turn on or off an output, you'll see the outputs light up or turn off. So it's a really good way to troubleshoot and figure out why your program's not doing what you expect. Now, so we've already seen another diagnostic type of indicator, and those are the LEDs on the input and output modules. This is another very powerful diagnostic indicator where you're monitoring the PLC while it is in operation.